Let's go over the answer for question number 7. Question number 7 is asking you to identify the best choice for the SN2 reaction and the SN1 reaction and to explain your answer. Let's go over the difference between a protic solvent and the aprotic solvent. For the protic solvent, they function as hydrogen bond donors. Most common protic solvents contain the OH group. For example, we have ethanol, water, and low molecular weight carboxylic acid, for example, the acetic acid. Aprotic solvents do not serve as hydrogen bond donors. An example of this type of solvent is dichloromethanes and the diethyl ether. Now that we know just the basic difference between the protic solvent and the aprotic solvent, let's identify the best choice for the SN2 reaction. And for us to answer this, we need to go back to the reaction mechanism for the SN2. We know that for SN2 reactions, we will have a primary haloalkane and we will have a nucleophile. A nucleophile, the best nucleophiles for SN2 reactions, or the most common type of SN2 reaction, involves a negatively charged nucleophile. And this nucleophile will do a backside attack to the carbon with a partial positive charge. The halogen has a partial negative charge. And as the nucleophile is doing a backside attack, then the halogen will now be your leaving group. How does the transition state look like? We have the carbon with a partially broken bond to the halogen. The halogen is not completely gone, so let's just have a partial negative charge on the halogen. And the nucleophile has a partially formed bond with the carbon. So let's have a partial negative charge on the nucleophile. And then after the transition state, we will have the halogen now as your leaving group with a full negative charge, and then we will have your new bond between the carbon and the nucleophile. Okay, for SN2 reactions, everything happens in the same step. As the halogen leaves, the nucleophile is attacking this carbon from the opposite side. So we need all the power that we can get to the nucleophile. You want to imagine it that way. Meaning you do not want to cover up this negative charge because you need the nucleophile to do its job. So the stronger the solvation of the nucleophile, meaning if you cover that negative charge up with the solvent, then you will need more energy to remove the nucleophile from this solvation shell provided by the solvent to reach this transition state. By doing so, the rate of the SN2 reaction will be decreased. And we don't want that. We want a fast SN2 reaction. So for fast SN2 reaction, you do not want to use a solvent that will provide strong solvation, that will not cover this nucleophile up, if you want to imagine it that way. So if we choose a polar aprotic solvent, that will be the best choice for SN2 reactions because they solvate the anions in a poor way, meaning they do not provide a strong solvation to the nucleophile. And by doing so, the nucleophile is free to do its job, to do that backside attack to the carbon with a partial positive charge. And when you use polar aprotic solvents, the rate of the SN2 reactions will be higher than using a polar protic solvent. If we take a look at the SN1 reaction, for the SN1 reaction, we know that the rate determining step is the formation of the carbocation. For example, if we had this haloalkane, this will be your carbocation here forming. And you will have the halogen as the leaving group with a full negative charge. We want to keep these two charges separated. So the nucleophilic substitution by the SN1 pathway involves the creation of these two charges, these two unlike charges, and the separation of these charges, of these opposite charges in the transition state of the rate determining step. And because of this, the rate of the SN1 reaction depends on both the ability of the solvent to keep these charges apart and the ability to make these charges stable by solvation, meaning we want the solvent to kind of cover